This video presents our work, Policies with Sparse Inter-Agent Dependencies in Dynamic Games, a dynamic programming approach. In multi-agent dynamic games, such as traffic routing, drone-based search and rescue, and autonomous power grid control, it's common to implement full-state feedback policies, where each agent's actions depend on all other agent states. However, obtaining full-state information can be costly or impractical, and inaccuracies in state estimation can make such policies brittle. To this end, we present a dynamic programming-based approach for computing group sparse feedback policies that selectively depend on fewer agent states in non-cooperative dynamic games. We first demonstrate our approach in linear-quadratic LQ games, where players minimize individual quadratic costs subject to linear dynamics. A solution to such games, known as Nash equilibrium, takes the form of linear feedback policies. One can compute such Nash equilibria via a dynamic programming procedure starting from the last time step and going backwards. At each dynamic programming iteration, the last step involves solving a linear system of equation SP equal to Y, where P represents the joint policy matrix containing all players' policy matrices. Instead of solving this linear system exactly, our method employs group Lasso regularization, penalizing the Frobenius norm of each block of the joint policy matrix. Each block corresponds to the state action dependence between particular pairs of agents, and the regularization encourages blockwise sparsity that zeroes out the entries in an entire block altogether, leading to policy matrices that depend on fewer agent states. The regularized policy matrix is then used in the next dynamic programming iteration. Our theoretical analysis shows that the resulting regularized Riccati recursion enjoys input-to-state stability under certain conditions and guarantees convergence. For more general form of non-LQ games, we extend the proposed approach via an iterative LQ approximating algorithm. We validate our method through multiple experiments. First, in a 4-player navigation game, each player is tasked to drive to their individual goal position while avoiding collisions with one another. Hence, the players need to coordinate and find an underlying equilibrium strategy. As players get closer to one another, our sparse policies consistently exhibit fewer inter-agent dependencies compared to standard Nash equilibrium policies, yet crucial interactions are preserved. Next, in an 8-player navigation scenario, we demonstrate that our approach readily scales to larger problems. Finally, in a 3-player formation control scenario, a leading agent tracks a trajectory while 2 followers maintain formation. The demo shows a ground truth Nash equilibrium trajectory. In the formal experiment, players are only given access to noisy observations of other players' states. Tuning the regularization parameter lambda provides a spectrum of sparsity levels. Higher regularization leads to greater decoupling between agents and trajectories less sensitive to noise. Quantitatively, we further find that in noisy settings, the regularized sparse policies by our approach always yield lower game costs than the standard Nash equilibrium policies. To summarize, we propose a dynamic programming-based method for efficiently computing approximate, sparse Nash equilibrium policies that selectively depend on fewer agent states via group Lasso regularization. For more details, please visit our website.